Hi everyone. So in today's video, I'm going to go over the DeepSeek V3 and R1 papers. I won't go over in perfect depth, but this is a talk I'm going to give somewhere else. So I just wanted to record it, give a demo run, and also have it for my YouTube channel. So yeah, we'll start off with DeepSeek V3. So DeepSeek models have been making quite the hype nowadays. DeepSeek V3 is the base model. They also have an instruction tune model, but the equivalent model you could think of is something like GPT-4o or Claude Sonnet. So these are the equivalent models. In terms of the overview, it uses a mixture of experts architecture. So it has 671 billion total parameters with 37 billion activated per token. It is trained on 14.8 trillion tokens, followed by SFT and RL. In contrast, Llama 2 was trained on 2 trillion tokens, Llama 3 was trained on 15 trillion tokens. So it's right up in the alley of modern LLMs. It's trained in mixed precision with FP8. So as far as I know, this is the first public open weight large frontier model which is trained with mixed precision FP8. It's trained with only 2.788 million H800 GPU hours. So H800s are basically nerfed version of H100, which are available in China due to export control regulations. In contrast, Llama 3 70B took 7.7 million H100 hours, and 405B took 39.3 million H100 hours. So they use a lot of techniques validated with their older models and papers like DeepSeek V2, V2 Coder, and so on. The run only costed them approximately $5.6 million. So this figure has been taken out of context in a lot of places. This is the cost of the final run, not of all the R&D and everything around it. Uh, so yeah, this does not include the GPU cost or anything. In contrast, Llama 3 405B has been estimated to the estimate for it is around $60 million. And finally, and most importantly, this is fully open weight. And why do we care about it? Because it has very impressive performance on benchmarks. So you can see on certain benchmarks like math and AIME and code forces, it absolutely dominates all the other frontier closed source models and open weight models. On other benchmarks like MMLU Pro, it's not the best, but it's quite close. And on certain benchmarks, it does lag behind. But overall, people have been vibe testing DeepSeek models, and also anecdotally, I've heard that a lot of them are in production even before this V3 release, like the Coder models and the V2 models. All right, and also you get very interesting posts. So this is a blind post where someone talked about Meta being in panic because their Llama 4 models, which were in training, are already behind benchmarks, and so there's a lot of panic in big tech. This is from a Reddit AMA where Sam Altman was asked if they would ever consider releasing model weights, which they don't in most cases, especially post GPT-2. But he mentioned that they're discussing it, and like they might be on the wrong side of the history. Also, there's a lot of controversy. So this is being called a Sputnik moment. The Sputnik moment is usually referred to the time when the Soviet Union sent the Sputnik satellites into space, and then the US quickly realized that the Soviets are not as behind as they imagined. In fact, they were even outperforming them in the space race. And then they started pumping a lot of money into academia and into NASA and created a lot of organizations. Also, since people do not understand language models very well, uh, there is like this senator in the US who's trying to get DeepSeek banned, so you could go to jail if you download a DeepSeek model. I don't think this will pass, but this was just a funny thing. So DeepSeek is like after a long while you have an AI model which has entered popular discourse. I think since ChatGPT, this is the biggest one. Also, one other vibe eval that I have is when my parents start asking me about these AI models. So post ChatGPT, this is the first time my dad has asked me about an AI model. So I think it has made quite the news. No, I don't know if it's for the right reasons though. So how long did it take the DeepSeek team? So they started off with the first paper in Jan 2024. I don't know how long it took them to do all the experiments for this paper, but at least in terms of like the paper release dates, their first LLM uh, release was in Jan 2024. They quickly followed it by their mixture of experts model in Jan itself. So these are papers oriented towards pre-training. Then they worked on post-training. So they created a math model, which was better than state-of-the-art math models. So they worked on creating a post-training pipeline. And they also created a coding model, which was better than like GPT-4 Turbo as well. And finally, they also released the second base model. So this was all in the span of like 7 months, 6 or 7 months. And as for the model sizes, it started off with like a 7B and 67B models. They went smaller with the MOE. They tried 2B, and they also went bigger. They also went all the way up to 145B. With the post training, they looked at 7B and 16B models, but with the DeepSeek V2 models, which were 236B parameters, they started hitting like the big upper, uh, like the pushing onto the bigger model scale ranges. And finally, you have the V3 and the R1 models. So the R1 models are based on top of the V3 models as the base models. And these are 671B parameters. All right, so now let's look at the design choices they made for the architecture. They use a mixture of experts architecture, and I'll quickly give you an overview of it. I'm sourcing these figures from this insanely good blog post. I would highly recommend reading it. But this is like a standard transformer. And if you zoom in to a decoder block, you see the structure. If you zoom in into the feed-forward network, you'll see that it's like a dense feed-forward network applied to each token hidden representation. Instead of having one dense model, you could have like multiple feed-forward networks, and you choose which one to use. So this is kind of like having different experts. So each MLP is an expert, and based on the query, you need a router which routes you to different MLPs. So in this case, since it's a numeric query, the numbers expert is activated. So this is a higher level goal of MOEs. Now you need a router to do this. How do you know which experts to use? And this blog post, like these animations, take one expert per layer, but in practice, usually you have several hundreds of experts and you take a subset of them. So you don't just pick one expert. So the way people traditionally do this, given the query, you use a feed forward network to project it into a vector with the size as the number of experts, and then you apply a softmax, which tells you how much weightage should you give to each expert. Now you can just pick the top one, you can do a weighted sum, you can pick the top two, and so on. And your output is the output of the network weighed by the softmax output. So this is how MOEs work, and this is like a more spelled out version with the weights and the inputs described. So the expectation is that certain layers learn certain kinds of features, certain experts learn certain kinds of features better and are more proficient in them. And when queries which require those features come, those experts are then activated. This figure is from the blog again. The different colors denote which expert was activated for this particular token generation in a given layer. And you can see that some experts do activate on certain things exclusively, like for instance for the tabs and the spacing things, you see some common experts for the first token. In like these object-oriented programming snippets, you see certain experts and so on. But like people want these specialized experts, but in practice you don't get very clean separations. So this is an overview of mixture of experts. Now, the DeepSeek MOE is pretty much the same. I'll only tell you about the key differences. So this is the same as we discussed before. You have a router and you route experts, but they also have a set of shared experts. So these experts are always activated. So you have this dual connection plus the always on shared experts plus the routed experts. And then you have some measure of like you get the affinity of how likely is this token to go to this expert. Then you normalize it and pick the top k, like pick the top k and normalize it to get your basically normalized probabilities. So yeah, this is your DeepSeek MOE. In practice, they have 256 routed experts and only one shared expert. So this the design choice they made in this thing. Now, there is an important aspect of MOEs, which is load balancing. So, if during training you do not explicitly do any kind of load balancing, then people have noticed that these training runs degenerate. So, the model early on might pick one or two experts randomly and then perform updates for them. And then, since the other experts do not receive any updates, these experts become more likely to be picked again and again. And then only these few experts actually learn anything. So there are two ways to do this. One which has existed for a while, which is known as this complementary sequence-wise auxiliary loss, which basically computes the expert preference and the expert weight, which is like how, so the expert preference is the total expert weight average over the selected experts and sequence length. So how likely is this expert being, how often is this expert being selected? And then expert preference is basically how much more preferred is this expert over other experts. So this is just like a standard loss people use. The DeepSeek team also uses this, but they have a very low contribution of this loss. So they say that they use it to prevent extreme imbalance, but alpha is set to a very low value. The loss that they come up with, okay, so this is an easy way, but not the best way. They actually come up with a lossless way to do this. So this is an auxiliary loss-free load balancing thing. So if you remember, you had this affinity score and you only took the top k. So they also insert a bias parameter here. The bias parameter is known as the bias update. The bias parameter basically increments or decrements how the pickup rate of these experts, and then it's incremented and decremented based on how overloaded or underloaded the expert is. So if a lot of queries go to that expert, they decrease the bias with a hyperparameter gamma, which is the bias update speed. And if the expert is getting very low load, they increment it. So they find this to work really well in practice. The second key innovation that DeepSeek papers use is multi-head latent attention (MLA). So the key idea here is your key value cache grows during inference. So why do you need to have like dense key value matrices, like a dense key value cache? You could just down project first and use that latent in your cache. So what they essentially do is given the input, uh, they create these latents first, and they only need to preserve these two latents instead of preserving the entire key value cache. So this saves them a lot of memory. And if you look at multi-head attention here, compressed KV latent, the compressed latent KV basically is projected up to give you back the key values and do attention, but the KV cache does not grow as quickly as it does with multi-headed attention. So this is also just a figure. I did not like this figure, and I saw something similar in a YouTube video. So I basically drew it myself, and yeah, this is, I think, a more spelled out version of this figure. I hope the idea is clear. The idea is very simple. It's multi-head attention, but the keys and values are constructed, not constructed directly from the hidden state. They are first converted into these latent vectors, which are smaller dimensional representations. And these latent vectors are cached, and later you can use them to construct KV. They also have this multi-token prediction objective, which is to predict multiple tokens instead of just one token at a time. So the reason they do this is that due to this objective, you have more dense training signals. So they hypothesize that this may improve data efficiency. You're learning more from the same amount of data. And the representations are not just tailored to predicting one token, but they need to pre plan for predicting better future tokens. In practice, they only predict one extra token. So even though they have like this thing which can be generalized to like tens of tokens or as many tokens as you want, but they only predict one extra token. All right, so this is all about architecture. Now we'll go into the infrastructure and the framework. So they use 2048 NVIDIA H800s. Just to contrast, Llama 405B use 16,000 H100s. So H800s have half chip-to-chip data transfer rate due to export control, and they also use InfiniBand when operating across nodes. So this is their cluster. This is much smaller than like Meta's cluster or Grok's cluster. Now, in terms of the training framework, they use HAI LLM, which is their internal proprietary framework. The only reference you can find to this framework is in DeepSeek's papers, and they have a blog post in Chinese. If you translate it, there isn't a lot that they share in that blog post. They only talk a bit about uh, the kinds of parallelisms that they're using, but we already know that. The parallelism that they use in this paper is 16-way pipeline parallelism. So pipeline parallel is basically you take, say, your model has 8 layers and you have 4 workers. So each worker gets 2 layers. So you have to do some operations, communication operations at the boundary once you finish the first 2 layers to send outputs to the next worker and so on. So this is like the most naive way in which you can implement pipeline parallel. Uh, they come up with dual pipe, which is so there are better ways to do this, of course, as compared to this, but their way is, I think, the most efficient in terms of the pipeline bubbles. So the more bubbles you have, the lower your efficiency, and they come up with an algorithm which is very close to zero bubble. The second thing is expert parallelism. Since you have a mixture of experts, you do not necessarily need to have all experts on the same GPUs. So if you have expert parallelism, this setup where all experts are on one GPU basically converts to different experts on different GPUs. Finally, they have data parallelism. This is the simplest form of parallelism where you basically keep a copy of the model and its optimizer on every GPU. Then you send different pieces of data to different copies. They do their forward passes independently. Once they're done, they will aggregate and synchronize before performing the backward pass. So this will essentially keep all the models in sync. uh, Sorry, they will do this after performing the backward pass. So they will synchronize the gradients, and all the models will perform the same update. So they do something like an average of all the gradients across all the DDP ranks. So this is like very standard, well-known parallelism stuff. Apart from their pipeline parallelism scheme, which is dual pipe. So dual pipe has fewer pipeline bubbles, and it overlaps computation and communication. So this is very important in pre-training language models, or just doing any kind of work with language models. You do not want to wait for data to do the computation. So essentially, as computation happens, you also want to prefetch the data you'll need for the next step. So to do this, they have efficient cross-node all-to-all communication kernels. So essentially, these communication things happen via nickel primitives like all reduce and reduce scatter, these kinds of primitives across GPUs, and they come up with kernels to do that more efficiently to fully utilize InfiniBand and the NVLink bandwidths. They also do this thing which I haven't seen before, at least publicly talked about. So the execution of stuff on GPUs happens in the streaming multiprocessors. Okay, it's a oversimplification, but yeah. And they reserve some of them dedicated to communication. So they manually tune how many should be used for computation versus communication. They also meticulously optimize the memory footprint, and hence they can train without using costly tensor parallelism. So tensor parallelism is like one of the most dominant forms of parallelism, but they can totally skip it in their case because they have. So the reason why tensor parallelism caught up is because some of the earliest works started using it. It was easier to integrate into your training frameworks, and it, instead of sharding the model across layers, so different layers going to different things, it shards the models vertically. So every layer, say if you have two GPUs, then layer one's half of layer one is in GPU one, half of layer one is in GPU two, and so on. So it has a much higher communication cost. So this is a training framework. They also do mixed precision FP8 training. So E4 M3 is basically how many bits of exponent and mantissa they have. There are two popular like FP8 training representations, E4 M3 and E5 M2. So they picked E4 M3, which has more exponent and less mantissa, which has less exponent and more mantissa. So why do you do training in low precision? So this is from the H100 spec sheet. You can see that FP8 operations have 2x more teraflops as compared to BF16 or TF32. So doing a lot of operations in FP8 essentially makes your training much faster. But since FP8 has a lower dynamic range. Uh, the dominant way to do mixed precision training is to do your operations in lower precision, but store your outputs in BF16 or FP32. So they store the master weights, gradients, and optimizer states in higher precision. They have like their own fine-grained quantization method. They also realize that FP8 is too small for things like attention operator activations. So they create their own data type for that, which is just crazy because it's super hard to use these low precision data types. Creating your own ones is just nuts because then you need to write everything from scratch. There's no support for something like this. They do a lot of manual tweaking, and in trial runs, you can see that they get close to 0.25% loss error as compared to BF16. So this is the general uh, mixed precision training thing where you keep your model weights in high precision, you copy them in low precision to do the forward pass, making it faster. Then you do your loss computation in high precision again. You do your back propagation in again lower precision. Then once you're done with your back propagation, then you again push your gradients into higher precision, do your operations using those higher precision gradients on the full precision model, and repeat. So I picked this diagram because I found this diagram to be a bit harder to explain. But once you have an idea about how this is happening, then you can see, okay, whenever you're sending inputs to an operator, it's in FP8. But whenever you're getting outputs, it's being accumulated in FP32 and outputted in BF16. So this is all there is to mixed precision training. Now, I'll talk about the pre-training part, especially the data thing. So they added more languages apart from English and Chinese, which they have in their older models as well. They don't explicitly outline which languages, but based on the benchmarks, you can take a guess around which languages they use. So there's a bunch of languages. I did not list them all out, but I think they're using some mixed multilingual sources and not specifically tailoring for certain languages. They have more maths and coding samples. They used 14.8 trillion high quality diverse tokens. They also use fill in the middle strategy, which is very useful for inline code suggestions. So the problem with inline code suggestions, if you want to use like an autoregressive model, is a lot of time when you're getting coding suggestions, you're getting that in the middle of the file. So the model can only see the past stuff as context and not all the code you have down below, which is also relevant if you're making some changes. Maybe you have a function which is being called down below. So the schema they use to like format these samples is they have these special tokens where they first add the prefix and the suffix and then the middle thing. So during inference, once your model is trained, you can give the prefix and suffix and then ask it to predict the middle tokens. And this is applied at the rate of zero point 0.1, so like 0.1% of training samples. They have a 128K token as a vocab, which is very standard. They have these are just the model hyperparameters. They have 61 layers, one shared expert, 256 routed experts. They do not have all MOE layers, so the first three layers are feed-forward networks. They are not mixture of experts. They set the multi-token prediction depth to 1. And this is, I think, another very interesting thing that they do. So since you saw that they have 64-way expert parallelism and 8 experts will be activated for each token. So these 8 experts could be like in 8 different nodes, but across nodes, the communication is the slowest. So they also ensure that the top 8 that they pick belong to at most 4 different nodes. So as soon as you've picked 4 different nodes and maybe within your top 8 you have a token which is on a fifth node, then they skip it and pick something else. So this is like a high level summary of the model hyperparameters. Another thing is long context extension. So people do not directly train their model for like these 128K context length windows. They first train them for like a smaller context window like 4K and then uplift the context window via fine tuning. So in their case, they go from 4K to 3K to 128K. Yarn is just a method to do this, and they also find really good performance in needle in a haystack benchmarks where the model does perfectly on at least this benchmark. All right. As for evaluation, so up until this point, they've just created a base model. This is not an instruction tune model, so they compare against other base models. So it performs V2 base. It also outperforms Qwen 2.572B, which is again a very strong model which supports Chinese. So it's from the Alibaba group, and the DeepSeek V3 has half the activated parameters against Llama 3.1405B base model. Which has 11 times more activated parameters. DeepSeek V3 again shows superior performance in like a lot of things, and it's competitive in other benchmarks. So overall, they have a very strong base model. Some interesting things that they found is the multi-token prediction really helps. The loss-free balancing strategy that I was talking about, where you have this bias, that consistently achieves better model performance, and it also shows better expert specialization patterns. All right, so this is some of the applications that they do. Now let's talk about post training. So post training usually has multiple stages. So I'll talk you through how do you train an instruction following model. So this figure is from the Tulu 3 paper, and Allen AI has a set of 4 papers which are extremely good around how do you post train modern LLMs. So I wouldn't you don't need to think about everything, but you first take a base model, you first do supervised fine tuning to create your SFT model, and then you use reinforcement learning to align it. So this is like the standard process. Now with reinforcement learning, different people use different techniques. For instance, Alan AI uses a lot of DPO, PPO, and RLVR, which is something they built. uh, OpenAI started off by creating PPO, so they use PPO a lot. At least they said they did. We no longer know what's happening. And DeepSeek created GRPO, which is a variant of proximal policy optimization PPO. So they use that. I'll give you a brief overview of GRPO later. So this is like the standard pipeline. So the first stage is supervised fine tuning, and here they just create these data sets for instruction following, non-reasoning tasks like creative writing, role play, so on. And they also use reasoning tasks such as math, code, logic puzzles, and they generate the data using DeepSeek R1. So we're not sure if this is the same model as the model they later released in the DeepSeek R1 paper, but this is like an internal model that they have. Uh, so this is an internal DeepSeek R1 model. I'm pretty sure this is not the same model that they release, because they have right now it has poor formatting and tends to overthink, which they did fix in the R1 paper to a higher degree. So they fine tune over this for 2 epochs, and they get their SFT model. Now they need to do RL based alignment. So at this point, I will ask you to take a leap of faith with me. The reason being, it's very hard to cover how RL based alignment works in like 5 or 10 minutes, or even like an hour. It would take longer. So what I would rather do is we know that RL based stuff has been used for a lot of things. It has been used to play games, it has been used to design robots, and so on. So what I feel is the most difficult part with understanding RL based alignment in language models is to understand how do constructs in the language model space map to things in RL terminology. So what's the state, what's the actor, who's the agent, what's the reward, and so on. So I will build that mapping, and then once we have that mapping, I think we can safely assume that any algorithm that you can use to train an RL model can be used to train language models as well now. So the mapping is the harder part. The algorithms already existed pre-language model as well. So the RL primitives that I want to map are the agent. So the agent is the language model itself. The state is the input tokens. So whatever tokens it sees in context. And the action is the token that it selects next. So this is like the most basic set of primitives. Then you have a reward model, which basically tells you how good or bad your action is, or how good or bad the picked token is. So it gives you a positive reward for good responses, negative reward for bad responses. Now, a lot of RL is just policy gradients, policy optimization. So in the case of language models, the language model itself is the policy because it models the probability of the action space. So the action space is the token space. So it models the probability of picking up the next token. So the language model is the policy that you optimize. And finally, we also use advantage function. So you don't need to think a lot about it, but the advantage function basically reduces the variance of the updates that you make during RL training. So you can think of it as, if I pick a certain token, how much better am I to do as compared to picking any token at random, or as compared to the average reward that I can get. So this is the advantage function essentially. And the other, so this is an example. For instance, the state Shanghai is a city in, and then the action is basically picking one of these tokens, and these are the probabilities associated with the action. So if you think of a grid world, you have like some creature in a grid, and then you have some probability over taking four actions going up, down, left, right. In this case, you have an action space which is basically equivalent to the vocabulary dimension. And finally, you also need trajectories, because you sample trajectories in reinforcement learning to use for optimization. So you sample trajectories from an old policy and look at how more likely is that trajectory under a new policy. So, for instance, a sample trajectory could be in the example before, where Shanghai is the state. You take the action by generating the token Shanghai. So this is now, this entire thing becomes the state, where is Shanghai, Shanghai, and then is becomes your action, and so on. So I've picked these examples from this really good video on RLSF, and I've linked it here. You can look at it, and it's like a 3.5 hours video. So this is the best I can do in like 3 minutes to summarize it. But this is how you map RL primitives to LLMs. And now once we've mapped this, we can use any RL algorithm which operates on top of these primitives, and almost all our algorithms do. So now let's look at what are reward models for LLMs. So usually there are two kinds of reward models: rule-based and model-based. So rule-based are things which you can validate using rules like regex, or some heuristics, like for instance, for math problems, you can just check the correctness. And for lead code problems, you can use a compiler to see if the code compiles, how many test cases does it pass, and so on. Model-based RM is usually used for free-form questions, where the reward model checks if the response matches the ground truth. And for open-ended questions like creative writing, where you do not have a ground truth, then the reward model just provides feedback on the input-answer pair. So you need to train a reward model as well. You can't really just use a weaker model to reward a stronger model, right? So in this case, they train a reward model using the DeepSeek V3 supervised fine-tuning checkpoint. All right. And this is their go-to RL algorithm called GRPO, Group Relative Policy Optimization. The main difference between this and the algorithm that this builds on top of, which is PPO, Proximal Policy Optimization, is that it does not have a separate model to predict the value of a state. So what do I mean by that? This algorithm basically samples a group of outputs. So you will generate, say, G different outputs from the old policy given a query queue. So you can do this by scaling the temperatures, changing the sampling parameters, and you get a bunch of outputs. Then you send this to a reward model and you get a set of rewards. Once you have this, the advantage, which is basically you use the advantage instead of a reward here, so that your updates have lower variance. You basically do a z-score normalization instead of finding out what is the average reward I can get in this state. So the value function tells you that, but they skip computing that and instead just generate a bunch of outputs and say, okay, this is the distribution of outputs I could get, and the rewards I get for these outputs is the distribution of rewards I can get. So I can now figure out which actions give me higher rewards as compared to all other actions, and optimize to make more those kinds of actions. I'm probably not doing the best job explaining this, but this is the high level idea. GRPO basically eliminates the use of a value model which predicts the value of a particular state. So since all of these algorithms are based on trust region optimization, so they are very conservative in their updates. So you can see they do not want to make very big updates. If your update is very big, so if the actions, if some action or some output becomes significantly more likely under the new policy as compared to the old policy, then it does not allow that to happen. It clips the update to a certain range. So you cannot make more than epsilon, like you cannot change by more than epsilon at a in a given a single update. And they also have this scale divergence between the original model. So this is like the standard SFT model. So your model does not become too different as compared to your SFT model. So this is all GRPO. Uh, I would highly recommend reading the DeepSeek math paper because that is where they introduce GRPO. The DeepSeek V3 paper doesn't explain GRPO in depth, but the math paper is really good around GRPO. And they validated GRPO in the DeepSeek math paper. As you can see, they trained a math model, and they found that using high quality data with GRPO can give you very high performance, even close to GPT-4 with a 7B model. So this is their prior validation of GRPO. And as I was comparing PPO and GRPO, in PPO you also train this value model, which basically uses the value of that particular state to center the rewards. You do not need to do that with GRPO. So you can directly compute the advantages using the different samples that you get from the model. Now, in terms of evaluation, of course, this model wouldn't be making uh, rounds on the internet if it wasn't good. So I wouldn't like go into every number, but the highlights that this is close to the peak. You can see that there's a lot of bold stuff in the DeepSeek V3 column. And on other benchmarks like Arena Hard, it does very well. On Alpaca Eval, it does very well. And on Bench, it does very well. So these are all different benchmarks and it does well on all of them. Some interesting results are distillation improves performance but increases response length. So when you were distilling from the R1 beta model, the performance without it declines, but your responses also become much lengthier if you use it. And the second token prediction is also pretty good. So it's similar to just sampling directly from the main model in 85 to 90% cases across generation topics. So it's quite reliable. All right. So this is done. We're now done with the base model. And now I'll take you through the reasoning model, which is the R1 model. So an overview, a reasoning model, this reasoning model is built on top of DeepSeek V3. So it's not like a standalone model, but it's post-trained on top of DeepSeek V3. Apart from it, it's very close to closed source models like O1 and Gemini Thinking. I really like this model because it's open weight and the technical report tells you what works and what doesn't work. It's also the first paper to show how far you can go with pure RL without supervised fine tuning for post training. So if you remember the pipeline I showed before, you first do supervised fine tuning and then RL alignment, but there was no convincing reason for why you couldn't do this the other way. Or like there was just speculation, but I don't think anyone at least wrote a paper about it. And they also release a wide range of models distilled using data from R1. So once they have this reasoning model, they uh, distill that into smaller models using just sampling from the larger model and training the smaller models on that. So what is a reasoning model? So these are models trained to explicitly outline their thoughts like O1, O3, Gemini 2.0 thinking, QWQ, and DeepSeek R1. As an example, this is something from the QWQ model paper. So the query is find the least odd prime factor of 2019 to the 8 plus 1. And you can see it starts to think about the problem. It realizes that maybe I can look for patterns. So it tries to fit it into this kind of expression, but it realizes that it cannot. Then it tries to see maybe I should try to see if there are any small prime numbers that divide it. So it tries to see modulo for different numbers. That doesn't work. It realizes, okay, continuing this process is tedious. Let me think differently. Maybe I can consider the expression and see it expressed in a form that reveals its prime factors. So it tries to use the Sophie Germain identity and it tries to manipulate it, but it again realizes that it doesn't factor nicely. It then thinks in a lot of different directions and finally it comes up, it reaches a direction which is promising and it pushes into that direction and gets the output. So this is how these reasoning models work. Now, how do you train a reasoning model? there are two models that train. The first one being DeepSeek R10, which is purely RL. So what they do is they take the V3 base model. They do not take the SFT model. They employ GRPO, which we just discussed, and they train the model to improve its reasoning. So they find that this model naturally emerges with powerful and interesting behaviors. For instance, on the AIME 2024 benchmark, the performance increases from 15.6% to 71%. And like with more things like voting, it goes to 86.7%, which is quite close to OpenAI O1. So now let's see how this exactly works. So they basically give the model this prompt. So a conversation between user and assistant. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process and then provides the user with the answer. And then the reasoning process are enclosed within these tags and these tags respectively. So the reasoning process and the answer. So then they give the user prompt, which is the question, and the assistant needs to generate first the thinking stuff and then the answer. So they enforce the model to put its thinking between think tags by a reward. They also give rewards for accuracy. So they do not have any neural reward models because they find that these models are very susceptible to hacking, but they have only rule-based rewards, and they find very interesting results. So I'll first look at figure 3, where you can see during the course of training, the average generation length of the response increases. So it goes from like 700 tokens all the way to close to 10,000 or even hitting 12,000 tokens in some cases. In terms of the performance, you can see that the accuracy uh, also increases over time as it generates more tokens. So you can see that uh, if you look at the performance of R10 with generating 16 and taking a consensus over those, it outperforms the OpenAI O1 0912 thing with consensus at 64. And even on other benchmarks, you can see it's quite competitive with O1 mini and outperforms even O1, the full version in some benchmarks. So this is like the first open weight frontier reasoning model. This other moment is also very famous, the aha moment, as they call it. So they do not explicitly train the model with any kind of ground truth data about how the model should reason. The model develops it all on its own. So it develops reflection and exploration, and it also has this aha moment which occurs during some intermediate checkpoints where it first approaches the problem in some way, and at some point it starts saying, oh wait, I there's an aha moment I can flag here, and then it starts to reevaluate and reach the correct answer. So this seems to be a very anthropomorphic way that the model has learned. So it probably saw something similar in its pre-training corpus, and then this kind of pure RL training emerged, uh, led to emergence of that behavior. Now there are issues with R10 since you do not enforce it to generate uh, the reasoning in a certain format. It has poor readability and also mixes languages. And when I read this, this reminded me of this tweet by Andre from last year. You can tell that RL is done properly when the model ceases to speak English in the chain of thought, because honestly, the models have no reason to speak in English. At least when they're thinking, they could be thinking in any way, and their final output could be in English. So this is just one uh, interesting thing. Once they did the R10 experiments, they had an idea of how to train a reasoning model. The R10 pipeline works really well, but it has a cold start problem. So the problem is that the model has never seen reasoning traces. So it derives its own way of doing it. And they solve this problem by collecting long chain of thought data, you by like from the R10 model or by few shot prompting models as with examples. Once they have this data, they uh, fine tune the model to basically do learn this particular way of thinking. And once they fix this cold start problem, then they find that uh, the model no longer has issues with readability, which R10 had, and R10 also often mixed languages, while DeepSeek R1 starts using this format which they enforce. And since they have human priors, it improves performance over DeepSeek R10. So it learns more quickly because the model does not need to explore a lot of things before figuring out what's the correct way to reason about stuff. In stage two, they do the same RL training process, but they have some additional rewards. They have a reward for language consistency. And they also find that due to this reward, the performance slightly decreases, but it becomes better aligned to human preferences and becomes more readable. And finally, they utilize the resulting checkpoint, so the output of this, to collect more supervised fine-tuning data around like writing, role-playing, and other general purpose tasks. And they use a subset of this data to again do supervised fine-tuning. And finally, they also do some alignment for helpfulness and harmlessness. So for helpfulness, the final summary should be concise and correct. And for harmlessness, the entire response to the thinking stuff as well as the final thing should not have like swear words or bad stuff in general. So this is their entire pipeline. This is a very simple pipeline when you think about it, and it's surprising that it gives such strong models. So in terms of the results, you can again see that there's a lot of bold stuff in the R1 column, and it does quite well as compared to O1 Mini or OpenAI O1 1217, which is like the bigger version. And congratulations, you now have a SOTA reasoning model that outperforms OpenAI's on several benchmarks. Finally, do you really need such a big model? Can you once you have like a big model, can you distill this behavior to smaller models? Is something they explore. And there is the way they do this is by directly fine tuning Quen and Llama models using samples curated from DeepSeek R1. And they do not use any RL based alignment, but they only want to see how far can they go with SFTs. So they also do not do any like logic distillation or anything. They just generate data using the reasoning model and fine tune the smaller models on it. In terms of the results, you can see these models do very well. Like the distilled 70B Llama model does much better than like the QWQ32B preview or OpenAI O1 Mini. So this is also like a very promising direction. Finally, they also tell us a bit about what doesn't work when creating a reasoning model. So there's been a lot of speculation around it. And Sasha Rashat, Cornell, has an excellent talk about speculations around O1 before R1 came out. I would highly recommend just listening to the talk. So the people tried using something called process reward model. So instead of just giving one reward, you should reward each step that the model makes. The issue is that determining whether the correct step is correct is very challenging. The model could be using some other route, or it could be listing out stuff in some other order. And this model is very susceptible to reward hacking. So as long as these deep learning models are not robust, your PRMs can never be robust. The other thing is Monte Carlo tree search, which is very popular in like AlphaGo, AlphaZero style stuff. But unlike chess, where you have a search space which is very well defined, token generation has an exponentially larger search space. At any given point of time, you can choose a much larger variety of tokens, and every time you pick a token, you again have just as many tokens to pick. While in chess, every move you make, your possible set of legal moves changes, and it's a much smaller list of legal moves. The value model also is very important in Monte Carlo research, but uh, training a very good value model is also very difficult for language models. So this is what they also release. Overall, both of these papers are really good. I would highly recommend reading them as well as like all the other papers by the Quen team. But yeah, this was all from my side. Thank you. And these are all the resources I've consulted. Maybe I'm missing a few, but these are all like excellent resources. So if you're interested, feel free to like go through these for the different parts of the talk. Thank you.